Yes, that's what I was here last week.
All right.
No, in this.
No. Welcome back again, everybody. We're going to discuss two things today. We're going to discuss the Carnot cycle or the Carnot engine. And we're going to introduce the second law of thermodynamics. We'll introduce the concept of entropy, how to calculate changes in entropy, and then how does the entropy relate to the second law of thermodynamics. Okay? So that's the goal for today. So a Carnot engine goes like this. Engines run clockwise or counterclockwise? Cycle.
Clockwise.
Always clockwise. Okay, good. So here's the Carnot engine. It goes between. It has four points: adiabatic, isothermal, adiabatic, isothermal, adiabatic. That's 4 points. Okay. So here it is. Here's an adiabat, and the temperature here is TC, T cold, it's called TC. And then here's another adiabat, and the temperature here along this curve is T hot. Okay? And then you would have, it's connected here by adiabatic, and this one is adiabatic. This is state 1, this is state 2, this is state 3, this is state 4. Those are the 4 states. And we're given the temperature here is TC, and here it's T hot. T cold, T hot, right? The red one is hot, the blue one is cold, okay? And the question is, find the efficiency of this engine. What's the efficiency of the cycle? What is the efficiency? So first, the efficiency, or actually let me state clearly, 1 to 2 is isothermal, 2 to 3 is adiabatic, 3 to 4 is isothermal, and then 4 back to 1 is adiabatic. Okay? So these are the 4 points. And the question is find the efficiency. Find eta. Now remember, eta, the efficiency, is the work done by the engine, what you get, versus what you pay for, which is the heat that enters into the cycle. Another way to write this is that you can write it as 1 minus QC over QH. And what is QC and what is QH? What's QC? Heat leaving the system. QC itself is a positive quantity. And leaving the system, then you can put a minus if you want to account for that. And then QH is the heat that enters the system. So we want to find this eta, and the only thing we're allowed to write the efficiency with is in terms of, we'd like to write it in terms of TC and TH. Right? How can we write the efficiency in terms of TC and TH? So this should provide us with good review for good review to all the processes we have been doing. All right, so let's start from 1 to 2. It's isothermal. So from 1 to 2, it is isothermal. What do you know about an isothermal process? The change in thermal energy is what?
0.
The change in thermal energy is 0, and first law says it is Q minus W, right? Q minus W. And that means Q is equal to W, and W for an isothermal process is what? The work done by the system here. W is work done by. Okay. What is that? V final over V initial, right? And in this case, the final is 2, the initial is 1. Okay. And what's the temperature? From 1 to 2, yeah, it's isothermal. What's the temperature? It's TC, T cold.
we
Yes.
talking about work by or work on?
Always by.
Always by.
Yeah.
So it's
W.
W.
Yeah, it's W by. Yeah. Efficiency has to be always a non-negative number, so it's work done by. Yeah. Okay. So work by. So question, is this quantity positive or negative? The work done by the system or the heat. It's negative because the volume decrease. So this is less than zero. So this is heat that enters or leaves the system? Leaves the system, right? This is heat that has left the system because it's negative. So QC, in other words, QC is the absolute value of this. QC is just the absolute value of that. So if you have a negative number, how do you make it positive? How do you take the absolute value of it? You have a negative number. Negative 7. What's the absolute value of it? Positive 7. So you stick another minus sign in front of it, so it becomes minus minus, which is plus, right? So how do I make this, and how do I take the absolute value of this? Well, it's already negative because V2 is less than V1. So if I put a minus sign here, putting a minus sign means basically you're raising this to the power of negative 1, which means you're just flipping the fraction. Instead of doing ln of V2 over V1, it becomes ln of V1 over V2. QC is N R PC ln of V1 over. Alright? Hope that's clear. Now, this is possible. We're going to do the next process, which is the from 2 to 3. 3, which is adiabatic. For an adiabatic process, we know we have the following. We have P initial, V initial with a gamma, P final. P final to the gamma, right? So, I would like things in terms of temperature. I don't want pressure to be in there. So, let's rewrite this pressure in terms of temperature. PV equal to nRT. So this would be nRT initial over V initial. So this is going to be written as this. nR initial over V initial times V initial to the gamma. This would be nR final over V final times final to the gamma. And this can be simplified by doing this. What's V initial to the gamma over V initial? V initial to the gamma minus 1. Good. So you can see this form here for adiabatic. It can be written also as V initial. T initial, V initial to the gamma minus 1, and then T final to the gamma minus 1. You can also write. Okay. So let's apply this to process from 2 to 3 because it's adiabatic. So we get E2, right? E2 to the gamma minus 1 is equal to E3, E3 to the gamma minus 1. And what is T2? PC, right? So PC, V2, we'll just call it V2. The gamma minus 1. EH, the gamma minus 1. And we'll write this as follows. TC over TH is equal to E3 over E2 over the gamma minus 1. Let's divide. And actually, because we have multiple equations that I'm going to reference, let's name this equation here equation 1, and let's name this equation here equation 2. I'm going to use the next board to do the next process, which is the next isoprocess, which is from 4 to 3. from 3 to 4. 3 to 4 is isothermal. And we basically would have this, something like this, right? So Q is equal to W and it's equal to N on T something, and then the one. So, right? So just the same logic as this, but I'm going to just start. So Q is equal to W and on T of something. Is it T hot or T cold?
T hot.
T hot. From 3 to 4 it's hot. Yeah, ln of V4 over V3. V4 over V3, right? And this is going to be positive. Good. So this is heat that enters the system. So this is QH. So this is QH. QH is equal to N of H ln of let's name this equation here, equation 3. In fact, I'm going to just draw it on the board. So from 1 to 2, heat leaves the system, and then from 3 to 4, heat enters the system. So from 1 to 2, QC left the system. From 3 to 4, heat entered. Okay. One more step, which is from 4 back to 1. So from 4 to 1, it's 80. So we're going to use this equation, right? 80. We'll just use the temperature one. So it would be T1 V1 to the gamma minus 1. T1 V1 to the gamma minus 1 is equal to 4 V4 to the gamma minus 1. Now what's T1? DC. Okay. DC. T1 to the gamma minus 1 equals to, and then T4 is T hot, right? T4 to the gamma minus 1. And so I get TC over T hot to T4 T1 gamma minus 1. And this is equation 4. Next, we're going to now get the efficiency. Okay. So let's see how we get the efficiency. I'm going to use equations 2 and 4 to simplify something, and then we get the efficiency. So use 2 and 4. Look at equation 2. Equation 2 says Tc over T hot is equal to something. Equation 4 also says Tc equal to T hot equals to something else. So those two things on the right, they must be equal to each other, right? The right side of this must equal to the right side, because the left sides are the same. So that means this. We got V3 over V2 to the gamma minus 1 is equal to V4 over V1 the gamma minus 1, right? Now, you can get rid of gamma minus 1 because something to this exponent is equal to something else to the same exponent. They're equal. So the inside is, or just raise both sides to the 1 over gamma minus 1. So what I'm saying is that this equation implies that V3 over V2 is equal to V4 over V1. Now you can cross multiply and rewrite this as follows. You can rewrite it as V4 over V3 equals to V1 over V2. You can rewrite this equation as simplify. V4 over V3 equals V1 over. That's the what I want. Okay, we're almost there. So efficiency is equal to 1 minus QC over Q dot. So 1 minus. That's right, QC. QC is at equation 1. Right? So QC is from equation 1. So it's N R PC ln of V1 over. QH is in equation 3. So it's NR PH ln of V3. These would cancel, and then furthermore the elements would cancel, because V1 over V2 is the same as V4 over V3, so their elements are the same. So this greatly simplifies, so we get the efficiency. 1 minus PC. So that's the efficiency. It's called the Carnot efficiency. Or the ideal efficiency.
All the way back to 1 and 2. What is working there? Yeah, what is working? Because it's for 5 is
Yeah, that's the one. V2 is less than V1. So the
Right.
volume decreases.
right, but when you use that starting equation, like Q from equals Q plus or 5, and
No. It's always Q minus W if it's the work done by the system. So the change, the first law is always this. Change in thermal energy. You can write it as Q minus W phi. It can also be written as Q plus W on. So that if the work is by the system, the minus sign is always there. The work done by the system, in this case, turns out to be negative. Okay. All right. Anyone else? Notice, the efficiency cannot, it's always less than 1, right? It's always less than 100%. Because TC is less than TH. Okay. So, we're going to now, how am I doing? 10 more minutes? Let's introduce entropy, and then get familiar on how to use it, and then relate this quantity called entropy to second law, and then we will, oh. Yeah, that's entropy.
Yeah.
So, let's start it fresh. Not really. Twice is always good. Okay. So. So, first of all, you have a quantity called entropy. You're not going to write the whole word every single time. You want to give it a symbol. And the symbol for entropy is S. Right? And it's defined this way. dS, small change in entropy, for a near equilibrium is equal to dQ over T. T is in Kelvin, and Q is the small amount of heat added or taken away. So from this definition, what can we say about the units of entropy?
Joule
Joules per what? Per Kelvin, right? T is temperature. Yeah. Q is heat. T is temperature. Where do we see there was a constant that had units of joules per Kelvin?
Specific.
Yeah. So KB would be was 1.38 units. So that's the entropy. If you want to find the change in entropy, you want to integrate the dQ over the temperature. And our next few examples will be on how to calculate this change in entropy. How to calculate the change in entropy, and then how we relate it to the entropy change, how we relate it to the second law of thermodynamics. So whenever you have a quantity, okay, it's defined. Why is it defined this way? Well, because it's related to the second law of thermodynamics. And then you want to know how to calculate it, how to use it, right? So you need to know how to use it. So let's do what the example I just erased was that. Here it is. So suppose we do the example where the temperature doesn't change first, and then we do an example where the temperature changes first. First example is this. Suppose you have ice at 0 degrees Celsius. And let's say we have 0.1 kilograms of it, 100 grams. And then this ice is going to melt at water at 0 degrees Celsius. Of course, 0.1 kilograms, right? It melts becomes water. And the question is calculate the entropy change from this process. Calculate the entropy change from this process. Start with the definition of entropy, or here's the change. So start with that. So the question is, find delta S. Right? Solution is going to have delta S. Now, what do you notice about the temperature throughout this process? It's constant. It didn't change. It stayed 0 degrees Celsius. So we can pull out the temperature. The integral of dq will just be q. It's the total heat that you add in order. You have to add heat, right, to melt the ice. So it will just be. So it's q over t. If the process is isothermal, then it will just turn out to be q over t. The process, the temperature doesn't change. Okay. How much heat was added to melt this? How do you find? MLO. Good. Mass latent heat of fusion over the temperature, right? 0.1. LF is something we can look up. Well, it will be given. It's 3.33 times 10 to the fifth, right? Hopefully I've used it enough to memorize it by now. And then T, should I put 0? Yeah, good. 273. So T should be in Kelvin. Temperature has to be in Kelvin. 70. So that's the answer. I'll just look it up. So I have 122. I will ask. So what do you notice about the entropy change? It's positive, right? So the entropy has increased, changed, increased. So does ice melt on its own and become water? No. Does that process happen spontaneously? Yeah. Does water freeze, just like you have water in this room, and then it just becomes ice? No. Yeah. So you have, so some processes happen spontaneously, others do not. Okay. So in the case for ice melting, if you put it in this room, it has gained heat from the room, and then it melted, right? So, but if you put ice in this, water in this room, the water is not going to lose heat somehow by itself. The room gets hotter, and then the water freezes. That does not happen. So, the second law states the following. It says this. So I'll just, it's very simple. The statement is very simple. It says the change in entropy of the universe is always greater or equal to zero. Okay, that's it. So, if a process, if you try something, if you say, if you make a claim, and then it turns out that process decreases the entropy of the universe overall, then that process cannot happen. That's it. It tells you what could happen and what cannot happen. So it puts further restrictions on the first law. The first law says, just as long as energy is conserved, I'm okay. This one puts further restrictions, right? So if, again, with the example of the water freezing, the first law is fine with the water losing, 1,000 joules of heat, it's freezing, and then the room gets hotter by 1,000 joules. Energy is still conserved. It's fine. The second law forbids that. Now, what is the universe? We will divide it into something that's manageable. Usually, it's you focus on the system and then the surroundings. So you break it down into this. Let's say you and then everything else. So you plus everything else, that's the universe. Okay. So that's how you break it. Usually you don't have to include that everything else literally. So it's just you and your surroundings where the process is happening. That's the fact. That's it. Okay. And then we will see, we will learn how to calculate. Okay. So our goal over the next few examples is to make such calculations. And I'm supposed to end in about a minute, right? Okay, so let me end here. We'll continue this on Thursday.